All right, now that we've had our hands dirty a couple times with the Dirac notation, let's exploit one of its other useful properties with regards to changing bases. As we saw, we can switch from position space to momentum space. That's kind of cool. What about energy space? And here we wish to derive the transformation from the position space wave function to the energy space wave function Cn of t, using the technique of example 3.9. Assume that the energy spectrum is discrete and that the potential is time independent. Cool. A lot of fancy words that we have here. Let's see how they all work together. All right, so what we saw within changing bases is that we know that we could multiply anything by 1 in the number system and get the thing back, so we call that the multiplicative identity. Whenever we're dealing with vectors or matrices, we have that 1 that's extended to I, and in all of these situations, I, the identity matrix, allows us to manipulate algebraically their definition, so we call these the resolutions of I. And that's what example 3.9 highlighted how to do. For us, let's take that a little more step by step and see what all these definitions come together to be. So here, we were told that we had an energy such that its spectra was discrete, so we can define the ket with all the discrete spectra, be the instate of the Hamiltonian, the energy operator, again time independent. And then we could say that if we want to get to the energy space, what we have is Cn of t. Well, that's the n, the state vector n, acting on the state of the system S. Okay, so here what we read is that we want the energy per the state in the energy basis. So, but nonetheless, let's see here that we multiply, or that we can multiply this blue S by 1. Here, the 1 is a factor of, it is not 1 like our scalar 1, but rather the identity for a matrix. And this is what we call the identity resolution. So if I plug this in, I get 1 out and I don't change anything except I have a new orientation. And that's wonderful. What we should note about this identity resolution is that we have this ket-bra thing again, which again goes back to what we learned earlier with the projection operator. So we're taking this state and we're transitioning whatever component into the x direction and then integrating it out to give us the energy that we want. So here we plug in this I here by splitting up the bra and the ket from the inner product notation. And you see we still have n to the left, blue to the right, and the identity right in the middle. No big deal there. We note here that integrals are linear, so we can use linearity. That thing keeps coming up again. Now you see why linear algebra is so useful for us. So we bump the integral outside and the dx to the other side, and we see that here this bra works with this ket, and this ket works with this, or rather this bra works with this ket. So we have n and x and s of t. And here, what we have to be aware of is that this now changes the bases to the x bases. And in fact, if we look at it, we define a state in a certain basis system where if we have the yellow x and the red x is the operator, where s is the state of the system, we say that the action of the position operator, because that's what's in the middle, in the x basis. So here, we're not operating on anything. This just represents the wave function in position space, of course, with time. And if we recall anything about this type of construction here, we see that this capital psi x of t has two solutions, the position and the temporal, or so the spatial and the temporal. So we have our energy baked into that function there. Let's also note here that the green and red, well, that is the energy in position space too. However, we need to switch this orientation because right now we want energy, we want the energy basis in, and so we want the variable x, but that's not going to give us anything. If we switch these two using the conjugate rule, then we see that we want the x basis giving us the energy information. And we have something for that, namely psi n of x. Okay, you still have this conjugate to put on here, so you see that we end up with the conjugate on the psi n, but you see here, this all includes, we get to the energy space, Cn as a from the position space using this identity resolution, and we're able to now integrate out all x, and thus we're just left with the energies, which are baked into the capital psi x of t via the spatial and temporal separation solution. So that's pretty cool. Again, the notation is really compact for a reason, and now we just have to be able to use it and interpret it. And I think, writing out these things a couple times will help with that. Clearly, color coordination helps, but definitely worth investigating because this kind of thing will be used frequently. Oh, excuse me. But yeah, pretty cool. Thanks for watching. Until next time, stay curious. Happy learning.